All right, welcome back. Today we need to talk about infinite limits. So an infinite limit is when a limit does not exist due to unbounded behavior. So this is like when we say the limit equals infinity, something like this, which remember doesn't mean the limit equals infinity per se, as in like it equals like x equals 2, because remember a limit has to be a finite number. So technically when we say a limit does not, when we say a limit equals infinity, what we are saying is, and let's just be really clear on this, I'll remind you a lot, this means that the limit as x approaches c does not exist due to unbounded behavior toward infinity. So that's a notational convenience to say that the limit equals infinity. Okay, but this will help us. That the notation is important, and we have a few properties here that will help us evaluate limits whenever we have unbounded behavior. So all the limits we've been dealing with lately in those analytic examples, where we were using the squeeze theorem, we were using the rationalize the numerator, the simplification, the factor and divide, all of those resulted in finite limits. But sometimes, even though you do that stuff, or maybe you can't do that stuff, and that's due to the fact that the limit doesn't exist, due to unbounded behavior. So these properties are going to allow us to work with these limits where the limit doesn't exist because of unbounded behavior. So let's see. We have three properties here. First one says, if you have two limits, and by the way, what's our assumption here? Our assumption here is that we have one limit that's infinite and one that's finite. We're approaching x equals c in both cases. So c, but we have two different functions, and so the limit of f as x approaches c is infinite, but the limit as x approaches c of g is finite. If you add those two, you can think about you're adding a finite number to an infinite number. Well, infinity wins. The limit's equal to infinity. If you multiply, if you multiply a limit that's finite and a limit that's infinite, well, you get infinity again. And then the quotient property is a little different because here we're assuming that the denominator is the infinite limit and the numerator is the finite limit. So if the numerator is finite but the denominator is infinite, well then that has to go to 0 because we have a finite number divided by a value that's increasing off to infinity, and so the answer has to be 0. Anytime you have a situation where you have finite divided by infinite, that limit has to tend towards 0. That's a very important property to keep in mind. We'll use this a lot. That if the numerator is finite, the limit of the numerator is finite, but the limit of the denominator is infinite, by the way, towards positive or negative infinity, the overall limit must tend towards 0. We'll use that a lot throughout the rest of the class. Okay. By the way, you have to be careful here with the signs. For instance, if you have a negative sign in front of infinity, well then you have negative infinity. Or like here, we're assuming that the finite limit is positive, but if the finite limit was negative and you multiply a negative value times positive infinity, well, you get negative infinity. Or if you have a negative finite limit and a negative infinite limit, well then you have negative times negative is positive. So you gotta be careful with your signs. But other than that, I think that's as long as you're careful with those, it's not a big deal. You can't really, I didn't want to write this theorem like 15 different ways for all the different cases. Basically, as long as you're careful with the signs, we can stick with the rules as they're stated and adapt as necessary. Okay? So let's see, we have a few examples here. Let's see what we can come up with. So example A, we have the limit as x approaches -4 from the left, by the way, of x squared plus 2 over x plus 4. Now, looking at all of these, it seems to me that basically getting these solutions depends on you knowing trigonometry and algebra. Specifically, it requires us to know the graphs of these functions. Now, we've talked about this before, I believe. If not, I'll talk about it right now, that it's assumed that you know what are called the parent graphs, or like these basic graphs from college algebra and pre-calc. For instance, what I mean by that is, like, the one that's necessary here is the graph of 1 over x. That's the parent function. So if you have y equal 1 over x, this is the parent function to x over x squared plus 4. Now, why is that important? Because if you know this graph, then you know this graph. And then you can know what the limit is. So let's think about this. If we take the limits here individually, using the sum difference rule, we'll get the limit as x approaches -4 from the left of x squared, plus the limit as x approaches -4 from the left of 2 over x plus 4. Now, the graph of 1 over x looks roughly like this. Yeah, we've talked about this before. This was back in the graphical limit section. I remember now. Looks roughly like that. Now, what about 2 times 2? Okay, well, if we're sketching by hand, to be honest with you, multiplying by 2, it just stretches it vertically a little bit. But if you're doing it by hand, it's really hard to tell. It basically it scales your y values by 2. But let's just say we're just doing this roughly, and so basically it's the same graph. If you have graph paper, yeah, you can tell the difference. Okay, here, I'll show in Desmos really fast. Because in Desmos, it's like you have a graph paper. So let's see. Here's 1 over x versus 2 over x. But if you're doing it by hand, again, it's hard to, you have to really be careful with your points and stuff. But look what happened. Basically, it takes all your y values. So instead of having a y value there of 1, you have a y value of 2. Instead of having a y value of what? 1, about 1/2 there, you have a y value of 1. It scales all your y values by 2. Okay. Now, what about if the denominator turns to an x plus 4 instead of an x? Well, that's when the transformations of functions kicks in. Because if you have instead y equals 2 over, let's see, x plus 4, what happens is that transforms the function. It translates the function 4 units to the left. So 1, 2, 3, 4. And so there's a vertical asymptote at -4. But then you basically draw the same picture. And now the answer should be evident. So if here in blue, here I'll box it off in blue, that is y equals 2 over x plus 4. And now we can obtain the limit. In fact, let's do this limit first. It's a quadratic. So we can always evaluate the limit, whether it's a left limit, a right limit, or a two-side limit. It's a polynomial, specifically a quadratic. You can always evaluate via direct substitution. So it's -4 squared, 16. Plus, but now what's the limit as we approach -4 from the left? Well, if we approach -4 from the left, we're over here. -4 from the left, we're going down towards -infinity. So this is an infinite limit, in fact, equal to -infinity, which the way you would know that was by knowing what the graph of 2 over x plus 4 looks like. But now we have this situation. We have -4 squared, that's positive 16, plus a negative, so that's minus infinity. So we have 16 minus infinity, which equals -infinity. -infinity. Okay, and if you want to verify this by looking at the graph overall, let's take a look. So we have x squared, the entire function is x squared. So that's your normal x squared. But what happens when you add plus 2 divided by x plus 4? And now we're taking the limit as we approach 4 from the left. Okay, 4 from the left. Oh, it's really hard to tell. But okay, here's 4. We're approaching 4 from the left, and watch what's going on here. As we get closer and closer, this graph is getting, notice how the x values are getting closer and closer to -4 from the left. So 4.1, negative 4.116, negative 4.109. So the x values are getting closer to -4, but this graph is shooting off towards negative infinity. It's negative 4.099, negative 4.095, 94. Those y values are shooting down towards negative infinity, which that coincides with our solution of negative infinity. B. Oh, we have the limit as x approaches 1/2 from the right of -3 over cosine pi x. You know what I would do for this? I would think to myself, I know what cos 1 over cosine is. If you divide by cosine, that's like multiply by what? Secant. So instead, I'd probably do this. I'd say equals the limit as x approaches 1/2 from the right of -3 secant pi x. Here, let's put parentheses there since we're handwriting. Okay. Now, this entirely depends on my knowledge of secant and what the graph of secant looks like. But I think if you remember from trig, shouldn't be a problem. So let's see. Let's do a little sketch of secant over here. Now, typically, you think about cosine, and cosine, looks like this. Oh, sorry, not like that. Looks like something like that, roughly speaking. But here's the thing. Usually cosine would have an x-intercept at pi over 2. And then again over here at 3 pi over 2. And then over here like at negative pi over 2 and at negative 3 pi over 2. But that's regular cosine. Here we have a scalar multiple on the input. Now remember what the input does. A scalar multiple on the input. The normal period of cosine, so you have y equals cosine x. The normal period is 2 pi. Okay, which means it's going to cycle between. It's going to reach one period in 2 pi radians, which if you think about like from negative pi to pi, like right here, negative pi to positive pi, like you reach back that same y value. Like there's a little valley there. It's called a relative extrema. Of the y value is -1. So like that distance between those two is 2 pi. That's the normal period. But whenever you multiply the argument by pi, it affects the period. In fact, if you multiply by a value larger than 1, you shorten the period. If you multiply by a value smaller than 1, between 0 and 1, then you get a longer period. But we're multiplying by pi, which is bigger than 1. So that means the period is shorter. Now, how do you figure out what the period is? Well, you take the original period, which is 2 pi, and divide by that scalar. So this tells me that the new period is 2. 2 pi over pi is 2. So that tells me that like instead of going here, instead of this being pi over 2 and that being pi, that's going to be 2. And this is going to be 1. Oh, and I did not want to erase all of that. So let's see if I can get this to rescale it. Carefully, come on. There we go. Let's rescale this. Okay, so this is going to be if we now have not cosine x, but cosine pi x. This is going to be a 1, and that's going to be a 2. Or wait, was that 2? No. Sorry, I messed up. The period's 2, which means this is going to be a 1. This is going to be a half. Negative 1/2, and negative 2. Okay. Now, so far we've been talking about cosine. Now, the reason I was talking about cosine is because that's how I get secant. Because secant, what you do is wherever cosine has an x-intercept, you put a vertical asymptote. Let's put a vertical asymptote right there. Let's put a vertical asymptote right there. Right here. Right here. And now the graph of secant basically takes all of the little peaks and valleys on cosine, and then you have like these parabolic shapes, like this. So here, red is secant. You go between these vertical asymptotes like so. Okay, so that is the graph of y equals secant pi x. So the black is cosine pi x. The red is secant pi x. Okay, so now we can use the property of limits, of infinite limits, because now we have, okay, -3. We can factor out, of course, it's constant, times the limit as x approaches 1/2 from the right of secant pi x. And now that we know the graph, what's the limit as we approach 1/2 from the right? Well, if we approach 1/2 from the right, that means we're over here on this part of the graph. 1/2 from the right means we're going down towards negative infinity. So we have -3 times negative infinity. Here's where I was talking about you have to be careful of the negative signs. We have a negative times of negative, which means we're going to approach positive infinity overall. Okay? Another way to think about that is this. If you go back to the original formulation, here I'll just solve it a different way. We'll have -3, and then like take the limit of the. Well, let's do the numerator and denominator individually. So let's use the quotient property, which says we can take the limit of the numerator as x approaches 1/2 from the right of -3. That's a constant, so that's easy. Over the denominator, limit as x approaches 1/2 from the right of cosine pi x. Okay, the top is a constant function, so the limit's -3. Let's think about this. If we want to look at the limit as x approaches 1/2 from the right. Now this time we're looking at cosine. Okay, we didn't rewrite it. We're looking at cosine. So this is the black curve down here. What does cosine look like if we approach 1/2 from the right? It's like right here. Let me get a different color here. if I like highlight right here, how would you characterize those values right there? They are below the x-axis, so they are they're negative, and they are very close to the horizontal axis, so they're very small. So here, this is not very mathematically rigorous, but what if I did this? -3 divided by very small negative value, a very small negative value. What do you think -3 divided by a very small negative value is going to be? Think like -3, think about this, like -3 divided by -0.1. That's what? That's -3 times -10. That's 30. -3 divided by -0.01. That's -3 divided by -100, or multiplied by 100, -100. So that's 300. Okay? If you don't believe me, punch these in your calculator. If you take a negative number and divide by a very, very tiny negative number, you get an overall very positive big result. And so you get infinity. So there's another way to think about it. I prefer thinking about it by rewriting this as secant and then looking at the graph of secant, but you can solve it either way. Okay? If one way makes better sense to you. With all of these, as far as like a test or an exam is concerned, the big thing you want to do is justify your answer. You need to make sure to justify it. And for these, I think, like I said earlier, the graph, the parent graph and knowing the graph is probably the way to go. Okay. Example C will be no exception to that previous statement. Limit as x approaches 0 from the right of x plus 1 over natural log x. Let's first take the limit of the numerator and denominator individually. So we get the limit. Oh, let's get our fraction. Bar the vinculum first. We have the limit as x approaches 0 from the right of x plus 1. On the denominator, the limit as x approaches 0 from the right of natural log x. Now, what's the limit of the numerator? It's a linear function. It's a polynomial. So we can simply take the limit via substitution because it's defined for all real numbers. And you get 0 plus 1, which of course is just 1, finite. But on the denominator, again, this relies on our knowledge of the graph of natural log x. The graph of natural log has an x-intercept at 1, and it looks like this. There's a horizontal asymptote at the origin. Sorry, not horizontal, vertical asymptote at the origin. So what's the limit as we're approaching 0 from the right? Well, we're going down towards negative infinity. In other words, we have finite over infinity, which the quotient property says has to be equal to 0. Has to be equal to 0. Here, let's check those last two. We checked A, let's check B and C. So B was -3 divided by cosine pi x. And we were concerned about the limit as we approach 1/2 from the right. Okay, so 1/2. Oh, we're going to make this a little bit bigger. Zoom out here. Let's put in a vertical line at 1/2. Because that is going to be one of our vertical asymptotes. So what's happening? As we approach 1/2 from, oh, was it right? No, I've forgotten. 1/2, yes, from the right. Okay, notice if we approach from the right, we're up here, shooting off towards positive infinity. Is that what we found to be true? Yep, positive infinity. That's what we found to be true. What about the next one? The next one was x plus 1 over natural log x. Now, if we approach 0 from the right, we are approaching 0. Notice, if we approach from the right, we're headed towards 0. Now, Desmos is lying here because 0 is not in the domain of that function, so there should be a hole at 0, 0. You know, like this. Oh, not like that. There should be a hole right there because we all know that 0 is not in the domain of a logarithm, at least a natural log. So that's what the graph looks like. And clearly from the right, that function is approaching the origin. The y values are trending towards 0. Okay, last one. We have, let's see, let's scroll down a little bit, get a little more room. We have x squared tan x, and it's the limit as x approaches pi over 2 from the left. Here, let's get a little room down. So you have the limit as x approaches pi over 2 from the left. That was x squared tan x. Okay, just like the first 3 examples, this one relies on your knowledge of tan, of the graph of tan. Okay, so notice we have a product of 2 functions. We can take the limit individually. Sorry, the limits individually. So let's, instead of having the limit of a product, let's do the product of the limits. So the limit as x approaches pi over 2 from the left of x squared times the limit as x approaches pi over 2 from the left of tan x. We're going to multiply those 2 answers. Now, this first one, x squared, that's a quadratic function. It's defined for all real numbers. There's no weirdness in that. It's a nice parabola. To find the limit, direct substitution works. So this is going to simply be pi over 2 squared is the first limit. Now, I don't really care what pi over 2 squared is. It's just a finite number is what we need to realize. A finite number. Okay? So, here, let's get rid of that 17 in there in the middle. Let's erase that. So that doesn't mess us up. Okay. So you have pi over 2. Now, what's this second limit equal to? Well, what's the limit of tan as x approaches pi over 2? We need to know what tan looks like. So let's see. Tan has asymptotes at like pi over 2, at say negative pi over 2, at 3 pi over 2, at negative 3 pi over 2. Then it has x-intercepts, say at the origin. Oh, let's first draw those asymptotes. So something like this. Asymptotes. And there's x-intercepts. There's one at the origin, pi, negative pi. So there's negative pi, pi. Oh. And then the tan looks like this, roughly. And this is not perfect, but it roughly looks like that. Over and over again. They should all be identical. My drawing skills aren't necessarily up to par, but basically like that. That's what tan looks like. So now looking at the graph, what is the limit as x approaches pi over 2 from the left? So here to the left of pi over 2, tan is doing what? It's shooting off towards infinity. So it's an infinite limit, and we have a finite pi over 2 squared times infinity. Tells us that the overall limit is infinity, is equal to infinity. Here, let's double check with Desmos. So we have x squared times tan x. And let's put in pi over 2, x equal pi over 2, since that is a vertical asymptote. Let's make it dashed. Now, as we approach pi over 2, what was it, from the left? Yeah, from the left. Yeah, notice this function is heading off towards infinity, just like we found the answer to be. But we found our answer using properties of infinite limits. Properties of infinite limits, and other prior properties of limits, like the product rule. Okay? We confirmed our result using the graph. So these properties of infinite limits are very important. And like I said, they oftentimes rely upon you knowing your algebra, knowing how to use parent graphs to transform graphs, and knowing your trig graphs and all that kind of stuff. So if you need to brush up on that, please do so. Like Google parent graphs, algebra parent graphs, and you should get, x squared, x cubed, cube root of x, 1 over x, 1 over x squared, e to the x, natural log x. There's like probably 12 of them that are pretty standard, plus your trig functions. There's 6 there, plus your inverse trig, which I guess that's 6 more. So there's a good 12 from trig class, and then I don't know, probably another 12 from algebra class that you should know pretty much off the top of your head. So if you don't, then make sure to add that of your list of things to review before we get too much deeper into this class. Okay, so that was properties of infinite limits. When you take a limit and you get infinity is one of your answers or part of your answer, before you get some sort of other answer, perhaps like we did with C. 0 is the answer, but one of the constituent parts was an infinite limit. Okay. Next, we'll tackle what happens again if you have limits that involve infinity, but in a little different way. So stick around for the next video. I'll catch you then. If you have any questions in the meantime, always feel free to reach out. Always here to help. I'll catch you in the next video.